she studied physics in the University of Oviedo in Spain. And then when she finished, she got a fellowship from the Spanish ministry to go to do some postgraduate studies in the Spanish theology at the SRF. And then there, she got in contact with synchrotron radiation, and then she really liked it, and she's here today. So she really liked synchrotron a lot. She, after her stay at the SRF, she moved to the Switzerland source where she did the PhD. And then her second postdoc, she moved to NSS2. After that, she moved to Diamond to beamline I-13, the imaging and beamline with she actually you came when they were still being built, no? Miriam, so you
I-13. No, I came already when we were taking users, and it was already like an operational one.
And then you moved to I-21 where you really participate in the building,
in the construction, yeah,
and the operation. And yeah, I mean, it's a pleasure to introduce her. And whenever you want, Miriam, you can start the webinar. Thank you so much.
Thanks a lot for the introduction, and also thanks a lot for giving me the opportunity to talk in this series. It's a real pleasure, and it's really good for us to be able to present the beamline and try to explain a bit more of what we are doing, and hopefully getting you attracted to do some resonant scattering. So I was thinking about like what would be the best for making the outline of this talk in this type of series. So I thought that the best I would try to like introduce what is like resonant scattering, like both talking a bit about elastic resonant scattering and inelastic resonant scattering, so that the differences are clear, and why is our motivation to build up this beamline and what we can take from this particular technique. Next, I will present the I-21 RIGS beamline, which is a very new beamline, state of the art for RIGS, and we have been operational since 2017. And finally, I will show some recent results from the beamline, some in-house work, some collaboration that we have done. And I have tried to, like, instead of getting in depth into one particular project, try to show a variation of different projects so that hopefully I can convince you that there's a broader range of physics or chemistry that it can be covered by this technique, and that we can, and that it can be really benefit by using this technique. So first, to start with soft X-ray resonant scattering. So the thing is, like, we are calling it soft because we are working into the soft X-ray regime, which is energies traditionally below 2000 electron volts. And this means that we are proving mainly the 3D electron system. So we have direct access to the LHs of the different elements. And because of that, the main focus historically of this technique has been on strongly correlated electron systems. Now, this slide, I like it a lot. One can find it in Science, and you can use it for your presentation. And I think that this is like fantastic to try to show what is the interest in strongly correlated electron systems. So for those of you that they are not familiar, so they are this type of systems like manganites, cuprates, so they are superconductors, ruthenite. They exhibit really rich phase diagrams with very interesting properties. So very small changes, either in doping, pressure, temperature, can induce totally different properties within the phase diagram. Yet it's not very well understood what is driving these properties to appear, what is inducing the changes with respect to the others. So therefore, this type of elements that have attracted a lot of attraction. Of course, properties like superconductivity, they have been investigated for decades. By now, we are not sure what is the full explanation for superconductivity, and still this is proven to be a very interesting field. But I hope by the end I can sort of show you that RIGS is also useful for other type of studies, not only for strongly correlated electron systems. But as I said, historically is the first thing that one sort of things when we are talking about resonant scattering and the study of these strongly correlated electron systems. Now, when talking about resonant scattering, you can have two types. You can talk about elastic resonant scattering or inelastic resonant scattering. The difference between those types is in the case of the elastic resonant scattering, so resonant scattering is a two-step process in which with the X-rays, the incoming X-ray, that usually is the LH energy of the element you're proving, then we excite a core state to an unoccupied state. Then, because this is an excited state and this is not stable, then the electron will decay back to the initial position and a photon will be emitted with the same value as the incident energy. That is the elastic process, and this is the most likely to occur. It has more probability by Fermi golden rule. This is the one that has the highest probability to happen. What happens when we study resonant elastic scattering, and then therefore is my title on this slide, it will be more appropriate to call it resonant diffraction, because what we use this technique in the elastic case is to study the ordering of the different electronic orderings in the type of the material. So we measure this type of electronic states that they are ordered in the reciprocal space, and then we measure at the Bragg condition for this type of electronic orders that otherwise they will be forbidden by the crystal structure. So we are combining a real space technique, which is EXAS, and a reciprocal space technique, which is Bragg diffraction. And by combining these both, we can get spectroscopic and spatial information. So we have site selectivity because we are measuring at the absorption edge of a particular element. And because we are fulfilling Bragg's condition, this requires ordering. So we can have enhanced magnetic charge and orbital sensibility, but also we get information about the ordering. And again, this is in the elastic case. So how this applies to the strongly correlated electron system. So the 3D electrons are responsible for most of the properties in this type of materials. And by proving in the LHs, we have direct access to the ordering of these 3D electrons. So we can get information about charge order, magnetic order, and orbital order. And this is quite important because RIGS, both elastic and inelastic, is one of the very few techniques with photons that they can prove directly antiferromagnetic order. And the only technique so far as I'm aware that it can prove directly the orbital order. In the case of inelastic resonant scattering, this is a bit different from the elastic case. So you have your photon in again with the LH value, you excite electron in the core level, goes to the valence band, but instead of decaying back so that it can come out of the excited state, then another electron from an occupied state from the valence band decays back to the initial state, and then a photon is emitted with the difference of the energy between these two levels. So of course, there's a loss of energy from the initial photon energy that it excites the initial core level to the one that is coming out. Therefore, it's called inelastic because there's some energy lost in this process. Now, a lot of different transitions could take place from the different energy levels of the occupied states on the valence band. And these will have different probabilities of happening. Then we have this RIGS cross-section of the Kramers-Heisenberg equation that could explain the different probabilities or intensities that we are expecting from each one of those. I don't want to get into too much detail into that, but all this can be explained theoretically. The important message perhaps is that, as I said before, the elastic transition is the most likely one to take place and is the most intense one. The inelastic one is much less likely to happen, and therefore the intensity that we have of the resulting spectra is very weak. RIGS is a very photon-hungry technique, but I will explain you later on, we have taken this into account when designing the beam and try to increase the fracs of the signal that we are measuring in I-21. Then another message is that there are two different types of rigs when we talk about it. You can hear talking about direct rigs or indirect rigs. If we are talking about direct rigs, which is what we are doing in the I-21 beamline because it's soft X-ray, then we are proving directly the transitions between the 2p and the 3d electrons, or 1s to the 2p. We have very good statistics and very good resolution for proving the oxygen KH as well. There's the indirect rigs that usually happens with hard X-ray resonant inelastic scattering, that it will get information about the DD excitations indirectly via the transitions between the 1s and the 4p. Still, a lot of information can get from this, but the theory behind it is slightly different, and one needs to get this into account when performing the experiments. So, of course, this type of information, they are always complementary to each other, and it's useful to be able to do both things. In the case of the stronger correlated electron systems, as I was explaining before, there's plenty of information that it can be learned using rigs. So here, this is like a theoretical spectra that shows like the different type of excitations that it could be observed in the low energy regime. So for instance, you can measure phonons. Phonons, they will be like collective excitations of the lattice. But in the case of strongly correlated electron systems, there's a very huge interplay between lattice and electronic properties. So very often, all the properties that we get from changes in the lattice, they reflect electronic changes, and they are very useful information for this type of systems. Then in a slightly higher energy range, we can get magnetic information, we can be sensitive to magnons. At a higher energy, we can get information about the DD or charge transfer. In this type of regime, then the energy resolution is not as critical as in the lower regime. So this is something in which I-21 has a strength because of the ultra high resolution, energy resolution. So we are able to resolve this type of low energy excitations. So we can see very well electron orbital electron-phonon coupling, we can see spin waves, we can see other type of collective excitations in the low energy regime. But as I said before, I want to try to convince you that RIGS is not only good for studying strongly correlated electron systems, but although it's a sort of young technique, if you want, we offer a lot of possibilities for the study of different type of materials and different type of physics or chemistry. So if you see resonant scattering put in perspective with different type of scattering techniques, of course, then they are all complementary to each other because there are differences about like the energy transfer range that each of them study. So in an ideal solution, then one can combine several of those techniques to try to get a full picture of a problem and try to get to an explanation of what is the physics underlying this type of question. In our case, then we can study very well energy transfer energies between 0.01 and 10 electron volts. And this usually provides us information about electronic structure and excitations. And I have tried to list here a list of problems in which we can shed light at the beamline, so that you see it's not only like superconductors, as I said before, you can also study large spin orbital coupling systems, heavy fermions and actinides, quantum spin liquids, itinerant band magnetism, molecular magnetism, one-dimensional quantum spin chain systems. As I said, orbital physics, because this is one of the few techniques that can directly prove the orbitals and not just simply get information indirectly from the changes on the lattice. We can also put information into van der Waals magnetism and spectronics, and I will show this later on with the in-house results. And recently, we have also proven that very interesting and important information it can be given on battery materials research with RIGS. Another important thing of RIGS that I wanted to highlight is we can obtain a lot of information from polarization analysis and from polarization dependence, because we are interested in multiples. So the electronic objects we are looking at, then they are not spherical. So they have a shape. So they are tensors with a rank, right? So in this case, you have a spin, or here, as I'm placing two orbitals, and they are forming some sort of unit cell. So if you see you're coming in with vertical polarization light, the way that the orbital A and the orbital B, they will be seen with respect to each other, and the projection, it will be different. So by analyzing the information that you are getting by changing the polarization, you can get information about how they are ordered within the space or how they are placed within the space. So if you see, if you change like the azimuthal angle of the sample, which is just simply rotating the angle along the specular vector of the surface, like this, the relation between the two orbitals still will be the same, but the projection that you will measure with respect to the incident polarization will be, in this case, you will get the same projection in both cases because of the angle has been changed. So usually it's very useful to measure at different angles of the sample with respect to the incident polarization and to change the polarization to get this type of information, and we can learn a lot. There are also like different rules and different transitions with the polarization from the different electronic objects, so we can learn a lot of information. Of course, and ideally, one would like also to measure the polarization of the outgoing X-rays as well, because some of these transitions in the material, like EE transitions or M1N1 transitions, they also can flip the polarization of the incoming light. And getting information of the outgoing polarization will also shed light into the nature of this different process, but this is something of our type of idea for the future to try to implement this type of outgoing polarization. At the moment, we are able to change from the incident polarization with no problem. So sort of like as a resume, if you want, about what are the advantages of soft X-ray resonant scattering, it's like it's element and orbital specific. We can choose to go in with a specific energy of a particular absorption edge, so then we can be sure that we are probing particularly one specific material. So this is very good for complex materials, because then we can be site selective and then obtain the information from a particular site. We are proving directly the 3D electrons, which are responsible for a lot of properties, not only in strongly correlated electron systems, but also in a very large field of research. We are sensitive to the X-ray polarization. And then one important thing is that contrary to, for instance, photo emission, we are bulk sensitive. Now, I'm very aware that one man's bulk is another man's surface, but with the energies that we use, we can penetrate about like 1,000 angstroms within the sample. So this ensures that we are not that sensitive to the surface of the material, and we are not a surface sensitive technique, and then we get information from the bulk. Of course, we cannot penetrate as deep as the neutrons, but still we are not a surface technique. We are getting information from the bulk. And because it's X-rays, then only a small sample volumes are required, which puts us in an advantage to neutron scattering, in the sense that we can study ultra thin films and we can study single crystals that they are very, very small. In the case of RIX, resonant inelastic X-ray scattering, it exploits both the energy and momentum dependence of the photon scattering. And in the case of the elastic type, like REX, is a Q-resolve technique, and it has access to orderings of the electronic system, so antiferromagnetic order, orbital order, charge order, and it has the ability to distinguish between the different order parameters, so that you can study whether you are having an order between this antiferromagnetic and orbital. They will appear at different Q positions in the reciprocal space, because they will correspond to different unit cells. So I hope that you get the idea of how interesting resonant scattering is as a technique, and this is what has driven us to try to build up the I-21 beamline at the diamond light source. So historically, and for a number of years, for the soft X-ray regime, like the driving force for RIX has been the resolving power. So if you see here, this is like ideal theoretical RISC spectrum that is similar to the one I have shown you before. So here you have like the elastic transition, that is the one that we call the zero. And then you have the different energy transfers that you can have, like photons, magnons, bimagnons. So you can see, I don't know, you can see as a function of the energy resolution, how this type of fixtures can start being distinguished. So initially, with a power of resolution of only 7,000, you get like a very coarse spectra in which you don't manage to see all the texture that is behind. So theoretically, at 40,000 power of resolution, one would be able to see the theoretical spectrum. And this is what it has been pursued during years for the different facilities to try to achieve that type of energy resolution. So this is like a plot between resolution versus the years and how the technique has been evolving. So of course, this is, as I said, this is a relatively young technique that started in the 90s. And here is what we are. We have a 40,000 energy resolution power. We can resolve this type of spectrums well, but of course, we always want to improve. So we are trying to work into a project into upgrading our beamline when Diamond will be upgraded for Diamond 2 in the next years. And hopefully we would be able to increase even further our resolution to try to achieve better information. So we are not just getting stuck where we are. We always want to try to like improve the beamline and try to give the best infrastructure that we can for the users. So this is a map of where you can find different type of resonant inelastic scattering beamlines in the world. So as you see, there are several places where you can find a beamline where you can perform the technique. However, there are only these 4 places currently where you can perform ultra high resolution soft X-ray rigs, which is the SRF, Diamond, the NSLS2, and in Taiwan as well. So this makes that because this is like very little instruments with this required energy resolution, our pool of users is very international. And we are happy to get very good users with very interesting science to be performed at the beamline at the moment. So this is the I-21 beamline currently at Diamond. As you can see, is fully operational. And if you want any more information about the beamline after this talk, please don't hesitate contacting me or anyone else at the beamline. You can find information in our webpage that is listed down here. And we can answer any questions you may have. I don't want to go into too many technical details about the construction, but I just wanted you to get the message like, this is a dedicated soft X-ray bricks beamline. So we know very well, like aligning the instrument, have it properly set up for doing this type of experiments is very challenging. And contrary to other beamlines, like for instance, used to be the case in BESI, we are not sharing the beamline with all the techniques or other instruments. So everything will be aligned for performing rigs and doing this with the best resolution and the best efficiency as possible. It's a dedicated beamline for rigs. We use a plain variable length spectrometer type of design. And we cover an energy range at the moment between 280 electron volts and 1,500 electron volts. However, the beamline has been planned from day 1 that eventually in day 2, we will arrive to cover 3,000 electron volts. That is a very interesting energy that will allow us to get to other type of materials like rutheniates or iridates that usually are hanging in the middle between the soft X-rays and the hard X-rays, and we will be able to provide information of them. Our aim was to have upgraded to that energy last year, but because of the COVID pandemic, we had to like delay a bit installation, but we are in the middle of it, and hopefully we will be able to reach this energy by between this year and the next year. So we have already started with some of the installation, and we are confident that by next year, we will be able to offer this capability for users. So the beamline polarization can be tuned between horizontal, vertical, circular plus, circular minus. We can cover the different angles with the linear polarization. And the total energy resolution that we have achieved is about 35 milli-electron volts at the copper LH, just close to 1,000 electron volts, and about 14 milli-electron volts at the oxygen KH, which is a very good resolution for oxygen. And I will show you later on, we have very good photon flux for the oxygen KH, which makes us in a way sort of unique compared to the other instruments with high energy resolution. The focal beam size, as I said, is quite small. We have only 2.5 microns in the vertical, which is the dispersion direction of the energy. So of course it has to be this small to ensure the energy resolution. And at the moment, our sample environment of what we use is just a solid state, because we have a very ultra high vacuum. We are measuring at -10, because like this, we are able to achieve temperatures as low as 8 Kelvin. So we can cover from 8 Kelvin to 330 Kelvin easily. We have installed a manipulator very similar to the ones used in ARPES. So we have 6 degrees of freedom, and we can move very well azimuthal and other type of angles and cover different regions of the reciprocal space quite easily and reproducibly. And the beamline has been in operation since December 2017. As I said, like the main driving force for rigs, it has always been the energy resolving power, and try to increase the energy resolution that we achieve. But another important factor is the photon flux at the beamline, because as I mentioned before, rigs is a very hungry technique. It's very photon hungry. The signal is very weak. So historically, one could like measure 1.5 hours per point. We have put an effort into designing the beamline to increase the flux that we arrive. And for this we have used a long sector at the beamline, we have a long undulator, and we have minimized the number of optics at the beamline. And this has allowed us to have at least like 3 times more flux than it used to be having in other type of high resolution beamlines. There are different things we have done to achieve the high energy resolution, that they are technical. If anyone is interested in getting more information on this, you can ask me. But I think I will move forward into that and not getting really into very mechanical, technical details on this. But this is very important. So in the soft X-ray regime, the heat of the X-rays is very high, it's not neglectable. We need to have a high stability of the optics. So we have needed to have like the line density of the gratings to be very high to achieve the resolution that we want. So we have different gratings with like 600 lines per millimeter, 1000 lines per millimeter, 2000 lines per millimeter. That they had been like studied, they are really flat, they are really high quality optics. But because of working in soft X-rays, we need to cool them using water, and then we need to clamp the water cooling system on the sides of the gratings. So of course, this induces some deformation into the gratings, and this has been a very thorough investigation of us together with the optics metrology group of Diamond, that they help us to come to the better or the best way of clamping method for this waterside cooling, in which we managed to minimize the distortion that it was induced by the cooling to the optics. So we have managed to achieve a combined surface error of like 1000 nanoradians, which this is really low. To keep it like this, then we need also to take into account the vibrational stability, like the flux of the water, whatever was induced into there and how it will affect as well. So we have managed to get a vibrational stability of around like 80 nanoradians for the pre-mirror of the monochromator and 40 nanoradians for the gratings. Apart from the stability and the energy resolution that comes from the beamline, from the insertion device to the sample, then we also need to take care about like the contributions to the energy resolutions of the secondary spectrometer. So this is from when we focus the beam into the sample until it reaches our detector. So for those of you that they are not familiar with rigs as a technique and how it's done experimentally, the difference of rigs with respect to other scattering techniques is like the outgoing scattering then is separated by a spherical grating monochromator that is placed after the sample. Then the scattering signal is collected and incised into the spherical grating monochromator, and then each component of the energy is separated in different vertical lines that they will arrive at different vertical pixels in the detector. And like this, we could distinguish one energy from the other. So of course, one needs to take into account the resolution from the gratings that they are placed in the spherical grating monochromator as well, as similar as it was with the first monochromator. And the detector spatial resolution is a very important factor as well. So if we go into details of that, so we have like a focusing mirror to try to reduce the beam size in the vertical as much as we can, like 2.5 microns, to ensure that the incident energy is as accurate as possible as we have managed to get. Again, similar to the PGM, to the monochromator at the beamline, then we have really worked into trying to optimize the grating slope error of the spherical gratings in the spherical grating monochromator. At the moment, the detector spatial resolution is one of these challenging type of aspects from the beamline, because there's not so much work into CCD detectors for soft X-ray regime. So currently, the only pixel size that we can achieve is about 25 microns. We have found different ways in which we can play with the aspect ratio of the pixel size by changing the angle of incidence in the detector so that we can improve this resolution. And I can explain this later on if anyone is interested. And again, we need to have a very high stability on the mechanics of the spherical grating monochromator. And as I show here, we have managed to find a stability of about 10 nanoradians. I should say, like, the support of the engineering group in Diamond achieving all this type of mechanical stability has been fantastic through all the construction process. And then we have benefit from their expertise into helping us achieving all this design and stability, and arriving to the point that we can achieve the energy resolution that we really needed. So we are really thankful for the effort of the mechanical engineers, Diamond, for supporting us through this project. So combining both, like the energy resolution, the flux from the beamline to the spectrometer grating. So we finally arrived to get a resolution, as I mentioned before, of 35 millielectron volts at the capital H, like 932, and 14 millielectron volts at the oxygen KH, with this type of combination of gratings. So we can combine different types of gratings, the beamline one and the spectrometer one, whether we need to have higher resolution or we need to have higher flux. So we are a bit flexible into choosing one combination of the other, depending of the needs of each type of experiment. But about the photon flux, one of the, I would say perhaps the most important thing that makes us different and has helped us to get a huge amount of flux is the fact that we have installed a collecting mirror inside the sample vessel. So it's a parabolic mirror that collects a solid angle of the emitted scattering and is placed as close as like 2 millimeters from the sample. This is challenging in terms of alignment, of course, because it's very close to the sample, it's very long, and we found out that if the center of rotation of the mirror is not coincident with the center of rotation of the sample, even a misalignment of like 50 microns can put the signal away from the detector. So we are that sensitive. So the alignment needs to be very careful. But with, even if we use only one of the collection mirror and not both, we already achieve an efficiency gain of an order of magnitude with respect to not using it. This is certainly not neglectable, and because of this efficiency and how we work it on the clamping of the gratings, we have found out that at the end of the day, our middle resolution grating is the best, let's say, as a working horse. Like, we have a good resolution and we have a really high flux, and most of our users are happy to use this because they can measure like a spectra that in copper, it could take them in other institutions in the past 3 hours. They can get it here maybe like 1 hour. So we save 3 times of of the beam time that is needed for collecting the data. This is how the signal looks into the detector. And if we use both collecting mirrors, it will arrive like 2 different signals at the detector, and they will correspond to slightly different positions in the reciprocal space. So we have worked hard also to try to implement the reciprocal space resolution in the beamline so that we are always sure of the positions and where we are. If the demands of the users are different and they don't care that much about the resolution in the reciprocal space, of course, integrating both beams at once, it even doubles your flux. So it makes that you can count even less time. So again, it all depends on each specific experiment and what is the need at each experiment. But if you can see here, this is like a regular Rick signal in a cuprate. And here, like, we have a variation of the energy resolution of 70 milli-electron volts. It's not even like high resolution. And we are already able to distinguish very well magnons and the DD excitations. This is only 1 minute acquisition. So like in the past, for getting such a spectra, you would have had to count maybe half an hour. So the flux is definitely one of our strengths in this case. So if I try to put all the information about the components that I have just mentioned before on the picture of the beamline itself. So there are a lot of things we have been taking into account to try to optimize our resolution. It has been a very incredible journey to design this beamline and build it up. So we have tried to focus in a lot of small details. For instance, we are having an external building because we can rotate like 150 degrees the arm so that we can get information about the different parts of the Bridgewin zone. So of course, if you are getting information about bands, the neutrons, they can simply get the momentum information because the neutron has a mass. Photons, they don't have a mass. We cannot get momentum information, but we can get this information if we change the angular momentum. So therefore, it's very important for us to be able to change the angle of the incident X-ray and the angle of the outgoing X-ray. So by covering this 150 degrees of the outgoing X-rays, we can really get information from a significant part of the reciprocal space in our experiments. So we needed an external building to place the arm and the spectrometer arm. And then this external building has been built up in analogy to how the synchrotron building has been built up. So it is a pilot floor that separates this floor from vibrations that it could come from cars or external movement outside. So it will isolate the vibrations by the pilot floor. We have a granite floor in which the spherical grating monochromator rotates, and this has a flatness of about 50 microns. If you understand, if we are changing the position of the outgoing angle, and then the spherical grating moves and the height is different, of course, the angles will be changed. We will need to realign at each time. We have managed to achieve a flatness of about 50 microns, which ensures that we can make continuous experiments at different angular positions without really losing our alignment. The mechanical stability is about 10 nanoradians, and our spectrometer arm is about 50 meters long, and it can rotate by 150 degrees. One of the things is why we can move it up and down, right? So like we can displace it like 100 in the up and down and to the different horizontal position, and is in order to increase again the flux of the beamline, we have minimized the number of the optics that we have placed. So for the spherical grating monochromator, we don't have a mirror like in the initial monochromator at the beamline. So because we don't have that mirror, we cannot direct the outgoing X-ray beam when it comes from the spherical grating monochromator to a particular path to arrive to the detector. And instead, for each energy that we are using, we need to search for the focal plane in which the X-rays arrive to the detector. So hence we need to move the detector up and down horizontally to search for this focal position for each of those energies. This is the reason why we have all this movement. The marble floor has a flatness from center to edge of around 200 microns. The spectrometer arm moves in air paths along this, ensuring this flatness and also keeping the ultra high vacuum resolution. We have a continuous rotation, so this the arm can rotate continuously the 150 degrees without breaking the vacuum. So experiments requiring different positions in the reciprocal space can already be performed at the beamline as well. Something as normal as the thermal stability of the building, it also played an important role in the energy resolution. And this is one of the decisions why the building has no windows, for instance. We have found out that we have reached thermal stability of around 0.1 degrees within 5 days. And this helped us as well with the energy resolution and the stability. At the very beginning, when we were building up, there was like a leak in one of the walls of the building, and we have a bit of thermal fluctuation, and we could see clearly how the signal in the detector was moving when the temperature was changing. So that effect is not neglectable at all, and is also an important thing if you really want to achieve this type of high energy resolutions. So as the conclusions about the I-21 beamline is like the first users were received in September 2017, and we have run over 30 user experiments already. The major upgrade of the continuous rotation sample vessel happened in August 2018, and in November 2019 we started with the first commissioning users to do continuous rotation experiments. At the moment, as I mentioned, then we are upgrading to 3,000 electron volts. We did the first part in June 2019. We were hoping to be able to complete it in 2020, but because of COVID pandemic, we are working on this at the moment, and we hope to have it complete by the end of the summer. Just the last thing is like this proposal submission deadlines is twice a year, it's 1st of April or 1st of October, and we are open to any type of proposals. And as the last part of the talk, I just wanted to show a bit of recent in-house results. Then I thought that rather than show you one particular complex case and getting in depth into that, perhaps that it would be better like I can show you a couple of different examples so that you can get a feeling about the different flavor of the science that can be performed at the beamline. Historically, like most of the users of RIGs, traditionally people associate RIGs with the study of high-density superconductors and cuprates, which is true, and a lot of the attention from this community has been put into RIGs during the years. Of course, we are really useful for this type of investigations, like superconductors are really interesting materials, they are strongly correlated systems, the phase diagram is really rich, there are a lot of different phases that they are not yet fully understood, and we can help to try to bring light into this type of problem. So as some examples of recent work that we have performed at the beamline on cuprates, so through our collaboration, we have studied charge density wave and phonons in cuprates. So we have studied the quantum fluctuations associated with charge order in a bismuth cuprate superconductor. Now, we were able to study the two energy regions, like very low energy excitations and a bit higher energy excitations, more corresponding to like around 200 milli-electron volt excitations. One of the main difference, because of course this type of materials have been studied by other non-resonant inelastic X-ray scattering or neutron scattering. But one of the main difference is like, although for the low energy regime, the results are very similar between the three techniques, for the slightly higher energy excitation values, then non-resonant inelastic scattering and neutral scattering, they measure the phonon self-energy, whereas RIGS phonon cross-section reflects the electron-phonon coupling and is interplay with the charge excitation. So we are sensitive to different phenomena. And because of this, the data we have collected for these higher energy excitations then look different than it was reported before with these other techniques. And looking into that, we were able to propose a new model, which we proposed that a dissipation-driven quantum melting of the charge order. And this would indicate that the relationship between the charge order and the superconductivity is beyond simple competition between phases, and there's a much more complicated interplay between them that needs further exploration. Another work that we have performed in cuprates is we use again charge density waves and phonons in this cuprate. We were able to study both in the copper LH and the oxygen LH, this type of excitations. RIGS is one of the few techniques that can prove the dynamic excitations on charge density waves. So this type of charge density waves in cuprates have been studied for a number of years, and a lot of information has been collected from the static part of these charge density waves. However, because there's not many techniques that can provide information about the dynamic part of these charge density waves, this is still some sort of a mystery. So with the power of RIGS to study this, we have studied this quasi-elastic charge density wave, the collective charge density wave excitations, and electron-phonon coupling in both the copper LH and the oxygen KH. And then our results, they indicate perhaps a multi-orbital nature of the charge density wave correlations. They might be universal to cuprates because of what we observe. And we were able to see that dispersive funnel-shaped charge density wave excitations might be generic in cuprates also. In this other case, like plasmons in hold-up cuprates, what we were seeing is like, usually when people study cuprates, you can study either they are electron dope or hole dope, and then they go by different parts of the phase diagram, whether they are electron dope or hole dope. And the studies that they have been performed in these materials, they show that there's an asymmetry in the electronic structure between electron dope and hole dope cuprates. However, even this asymmetry exists, the charge order is ubiquitous in both type of hole dope and electron dope. But a more like general type of collective excitation for the charge, and it will be the acoustic plasmons. They are not so easy to be observed so far. So they haven't been observed in the electron dope cuprates, but we have managed to observe them in these hole dope cuprates. And one of the surprising things, and probably gives the explanation why they haven't been observed before, is that they show predominant oxygen character despite being collective charge mode excitations. So if you see, we have measured in the copper LH and in the oxygen KH. So here is where the expected plasmon dispersion should be. We don't observe anything, but measuring exactly the same region in the KH, we really see that the plasmon is there. For some reason, is a predominant oxygen character of this type of acoustic plasmon, which we think is a very interesting result. If we go away from the cuprates, another interest of the community for the latest years, it has been the sort of quest, if you want, for finding a high TC nickelate superconductor. Ever since there was predicted that it could exist a nickelate high TC superconductor, a lot of groups that have been trying to find what it will be ideal material for achieving this. And then our collaborators in Stanford, they managed to find thin film of neodymium nickel O2, in which they observe superconductivity. And then we have studied electronic properties using RIGS to try to understand the behavior. And this is like very interesting because although there are some similarities to cuprate high-TC superconductors that we have observed into this electronic structure, there are significant distinctions that they should be not overlooked. So, for instance, in this neodymium nickel 02, it has 3D9 infinite nickel oxide layers, which is very similar to the cuprate. So it's analogous to the case of high-TC cuprate superconductors. But in this particular case, there's a three-dimensional metallic neodymium 5D state at the Fermi surface, which doesn't exist in the case of the high-TC cuprates. And there's a Kondo-Anderson lattice-like oxide intermetallic reference state. And this is totally different than the case of the high-TC cuprate superconductors, where the reference state is a Mott insulator. So although they are both superconducting, they are similar, there are these important differences that they should be addressed in the case of trying to follow this path and try to study further the high-TC nickel superconductors. Besides from all these superconductor materials, we also have found some results about a coherent many-body excitation in van der Waals antiferromagnet. So we know this sunrise singlet is formed by the correlation between localized d orbitals of a transition metal and the p orbitals of a neighboring ligands. So then this state that has been predicted long ago is quite, it was pursued. There was a lot of interest in finding and observing this type of state. Using RIGS, optical absorption and photoluminescence, we have managed to observe coherent excitonic sunrise singlet in this material, nickel phosphorus sulfate. And this is a rare report of coherent many-body excitation in real material. So we were very excited to observe these experimental results when we measure at the beamline. And finally, recently we have also proved how we can contribute to the battery research as well. So in this work with our collaborators from the Oxford University, we were studying the redox cathode in lithium-rich 3D cathodes. So there's a lot of interest in understanding properly how this oxygen redox mechanism work, because it has been observed that in this rich 3D lithium-rich 3D cathodes, although they are promising candidates for this type of battery materials, the problem is that the high voltage that is associated with the oxygen redox process on charge is not recovered on discharge. And this produces a voltage hysteresis and substantial loss of the energy density that is not optimal for using them as battery materials. So the first step was to try to understand this voltage hysteresis and what was happening during this redox process. So thanks to RIGS, we have managed to observe that this is linked to the structure of the material that is used. So we have observed that this is more likely to happen in honeycomb order type of material. And because when this redox process happens, the transition metal ions, they migrate from their positions. And then when they come back, once the discharge happens, they don't go back exactly to the initial positions. And this causes the energy loss. So this information is very important, because then one can try to design new materials in which one could try to minimize these migrations of the transition metal ions to try to improve the performance of these battery materials. So just like to finish, and I think I'm running a bit over time, like the take-home message that I wanted to try to pass you, and I don't know if I succeeded, is like RIGS is a very powerful proven spin, charge, orbital, and lattice excitations in materials across condensed matter physics, material science, and chemistry. RIGS has a high cross-section, micron beam size that is suitable for studying atomically thin films, artificial ether structures, microcrystals. in the future of something that we are looking forward to, something for Diamond 2 or in the future to try to achieve something else with the beamline, is that we could combine rigs with microscopy for studying the electronic inhomogeneity problem, or we could enable electric and magnetic fields and polarization analysis, and then we could use rigs to uncover new physics in many exotic systems as well. So this is something we would like to try to implement for the future, if possible. And with this, it's just like, this is the beamline people, all of us. Thanks a lot for like our collaborators in all this in-house work that I have presented. And thanks a lot for you for listening.
Thank you so much, Miriam. Thank you for this really complete talk. I mean, you went from the theory to the beamline, and then some very, very interesting examples in a lot of different areas that I'm sure are useful for most of the people that are in the webinar. There is no questions in the chat, at least yet. Oh, okay. So there is a question from Tom. Tom, do you want to ask a question live?
Yeah, I can do. Yeah. So the battery materials, when you have the vibrational rigs, that corresponds to the OO stretch, right? I think is that what was meant?
I think it's just like I'm not an expert on this research because I was not a PI on this. I could perhaps like maybe give you like the references and so on. We have published like a couple of papers, but to get like into more details, yeah. So what we see is that there's a difference between the different charges of the oxygen. So we can distinguish between them, right? Because they will correspond to either if it's -2 or not, they will appear at a different energy value, and then it will help you like distinguish them.
Okay, so this is obviously a diatomic, so it has one stretching frequency. How many from I don't know how many vibrational Rix measurements you've done, but you know, how many frequencies are you able to establish in maybe more complicated systems before essentially it just becomes broadened and then it just a full kind of, well, for want of a better word, a blob.
Okay, I'm not sure how to reply to this, because like my field of expertise is more like the strongly correlated electron systems, and this is more like chemist. I could try to find out the answer for you. I'm sorry.
Oh no, don't worry. It was a bit speculative, but yeah. Okay.
Yeah, but it's true that we have measured other materials like also organic magnets and stuff like this, that they are farther away from the solid state physics, and we still have enough resolution to solve them. It's just that they have not been published yet by the users. And
okay,
I couldn't show.
Yeah, cool. Thanks very much.
Thank you so much, Tom. I have a question, Miriam. It's very much, you know, it's a question with two sides. So the first one is about the enormous amount of photons that you're putting in the sample. So the 10 to the 15 photons per second is an enormous amount of energy, and in a very small footprint as well. So
you're breaking up on me. I cannot really understand you. Sorry.
Sorry. Did you hear me?
Now better, yeah.
Now better. It's just about the radiation damage in your sample.
Yes.
Photons in a very small footprint.
Yes. So this is a known problem, and this really depends from system to system. So for some users, they are really concerned about that, and maybe we study their materials as like this, because the beam spot is so small. If we assume that the system is homogeneous enough, what we do is from exposure to exposure, we move the beam through the sample so that we are hitting different fresh spots for each type of exposure to prevent for this. There are some materials in which we have seen that they are robust enough and you cannot really observe any beam damage, but you are correct, and this is an issue, and Therefore, this small beam size become handy, and the reproducibility of our manipulator to being able to move around and finding fresh spots of the sample for each exposure.
Then a second question, Miriam, is about sample environment. So
Yeah.
I mean, that's here, solid state, 6-axis manipulator, and then the low temperature. Do you guys have plans for, extending the sample environment to, I don't know, I mean, it's a little bit speculative, but to do some in situ measurements, for example, in the batteries or?
What we are doing so far with the batteries is that we have implemented a vacuum suitcase. So then in the case of this Oxford group, it's very convenient because they can come over to the beamline, pick up the vacuum suitcase, do whatever work they need to do, put the vacuum suitcase into their glove box, transfer, and then we transfer it directly to the beamline without breaking the vacuum. That is something that is possible. But of course, if the user will come from farther away, I don't know how effective it will be to send in the vacuum suitcase so far away. So then it will need to be implemented using any laboratory within Diamond. But yeah, once we started working into this type of materials battery, we discovered that having a vacuum suitcase was really, really important. Right now, we are very confident with it, and we have used it already in a number of experiments.
So all the experiments have to be in vacuum?
Yes. One of the main things for the vacuum, if you want, is not, what I will explain it is because of the collection mirror. The collection mirror, the parabolic mirror that we have inside of the vessel that makes us win that much flux, is really close to the sample. So when we are changing temperature, if the sample is degassing and the pressure is higher, then any contamination can be deposited in the surface of those mirrors. And then we won't be able to use them anymore. And this is one of the main reasons for preserving the ultra-high vacuum for all experiments. If we wouldn't have this inside, then perhaps we could sacrifice a bit the vacuum for other type of experiments. But currently, if we are giving importance to the flux, because this makes like a 3-hour spectra can be collected in half hour. So instead of having users for a full week, we can have them in 3 days. And it's really like an improvement. And we are giving sort of priority to this, and this limits to the use of solid states for the moment, or at least something that doesn't degas.
No, it's interesting. I mean, to see in which direction you guys are thinking about, going, and it seems that you are going to the microscopy, so that to include, with the small beam trying to work. So
I think it's like, for me, it's something like I'm very interested about the microscopy, and it will match with the question that you have just asked. Like a lot of the users are worried about the beam radiation, and then you move around in the sample, and then you're assuming that the sample is homogeneous. However, especially in a strongly correlated electron system, the competition between phases has been thought about giving rise to this type of particular properties. So how homogeneous they are. And therefore, I think it would be interesting to try to study in the macro regime and try to see how homogeneous indeed those systems are. Of course, this is not trivial, because then you will focus the beam farther, and then you could induce larger beam damage, at least if you, but one could use, like when I worked in elastic resonant scattering in Brookhaven, I worked at implementing a system using zone plates for doing this focusing. And because the zone plates, they also absorb part of the incident radiation, then the signal is weaker when it gets to the sample. So it could be one of the possibilities. I think it will require some thought.
It's really, really interesting and clearly very exciting science with the publications that you have shown. So thank you so much, Miriam, for this splendid talk. And just to remind you that we are going to stop the series of webinars until September, but we do have a mailing list. So Faye just have put the link in the chat. So if you are not registered, just register to the mailing list, and then you will receive all the